Like I said, just
in
think of
theory.
money as information. People often will think of money as having power in and of itself. Um, it does not. Money is information, and it does not have power in and of itself. Uh, again, applying the physics tools of thinking about things in the limit is helpful. If you are stranded on a tropical island and you have $1 trillion, it's useless because there's no resource allocation. Money is a database for resource allocation, but there's no resources to allocate except yourself. So money is useless. If you're stranded on a desert island with no food, all the Bitcoin in the world will not stop you from starving.
Yeah.
So, like just think of money as a database for resource allocation across time and space, and then what system it is what in what form should that database or data system what would be most effective? Now, there is a fundamental issue with say Bitcoin in its current form, in that the transaction volume is very limited, and the latency the latency for a properly confirmed transaction is too long, much longer than you'd like. So it's actually not great from a transaction volume standpoint or a latency standpoint. So it is perhaps useful as to solve an aspect of the money database problem, which is this sort of store of wealth or an accounting of relative obligations, I suppose. But it is not useful as a currency, as a day-to-day currency.
But people have proposed different technological solutions,
like Lightning.
Lightning Network and the layer 2 technologies on top of that. I mean, it seems to be all kind of a trade-off. But the point is, it's kind of brilliant to say that just think about information, think about what kind of database, what kind of infrastructure enables that exchange of
like
information.
you're operating an economy, and you need to have something that allows for the to have efficient value ratios between products and services. So you got this massive number of products and services, and you need to, you can't just barter. It's like, that would be extremely unwieldy. So you need something that gives you a ratio of exchange between goods and services, and then something that allows you to shift obligations across time, like debt and equity, shift obligations across time. Then what does the best job of that? Part of the reason why I think there's some merit to Dogecoin, even though it was obviously created as a joke, is that it actually does have a much higher transaction volume capability than Bitcoin, and the costs of doing a transaction, the Dogecoin fee is very low. Like right now, if you want to do a Bitcoin transaction, the price of doing that transaction is very high, so you could not use it effectively for most things, and nor could it even scale to a high volume. And when Bitcoin was started, I guess around 2008 or something like that, the internet connections were much worse than they are today, like order of magnitude. They're way worse, in 2008. So like having a small block size or whatever is, and a long synchronization time made sense in 2008. But to 2021, or fast forward 10 years, it's like comically low. And I think there's some value to having a linear increase in the amount of currency that is generated. So because some amount of the currency, if a currency is too deflationary, or should say, if a currency is expected to increase in value over time, there's reluctance to spend it, because they're like, I'll just hold it and not spend it because its scarcity is increasing with time. So if I spend it now, then I will regret spending it. So I will just, hodl it. But if there's some dilution of the currency occurring over time, that's more of an incentive to use it as a currency. So Dogecoin, somewhat randomly, has just a fixed number of sort of coins or hash strings that are generated every year. So there's some inflation, but it's not a percentage base. It's a fixed number. So the percentage of inflation will necessarily decline over time. So I'm not saying that it's like the ideal system for a currency, but I think it actually is just fundamentally better than anything else I've seen, just by accident. So
I like how you said around 2008. So you're not, some people suggested you might be Satoshi Nakamoto. You've previously said you're not. Let me ask.
Not.
You're not, for sure. Would you tell us if you were?
Yes.
Okay. Do you think it's a feature or bug that he's anonymous, or she, or they? It's an interesting kind of quirk of human history that there is a particular technology that is a completely anonymous inventor or creator.
Well, I mean, you can look at the evolution of ideas before the launch of Bitcoin and see who wrote, about those ideas, and then I don't know exactly. Obviously, I don't know who created Bitcoin for practical purposes, but the evolution of ideas is pretty clear before that, and it seems as though Nick Szabo is probably more than anyone else responsible for the evolution of those ideas. So, he claims not to be Nakamoto, but I'm not sure that's neither here nor there. But he seems to be the one more responsible for the ideas behind Bitcoin than anyone else.
So it's not perhaps singular figures aren't even as important as the figures involved in the evolution of ideas that led to a thing. So
yeah,
it's perhaps it's sad to think about history, but maybe most names will be forgotten anyway.
What is a name anyway? It's a name attached to an idea. What does it even mean, really?
I think Shakespeare had a thing about roses and stuff, whatever he said.
Rose by any other name would smell sweet.
I got Elon to quote Shakespeare. I feel like I accomplished something today.
Shall I compare thee to a summer's day?
I'm gonna clip that out instead of
Not more temperate and more fair.
Autopilot. Tesla autopilot. Tesla autopilot has been through an incredible journey over the past 6 years, or perhaps even longer in your mind, in the minds of many involved.
I think that's where we first connected. Really, was the autopilot stuff, autonomy, and
the whole journey was incredible to me to watch. I was because I knew, part of it is I was at MIT and I knew the difficulty of computer vision.
Yeah.
And I knew I had a lot of colleagues and friends about the DARPA challenge. I knew how difficult it is. Mm-hmm. And so there was a natural skepticism. When I first drove a Tesla with the initial system based on Mobileye, I thought there's no way. So at first when I got in, I thought there's no way this car could maintain stay in the lane and create a comfortable experience. So my intuition initially was that the lane keeping problem is way too difficult to solve.
Oh, lane keeping, that's relatively easy.
No, but solve in the way that we talked about previous is prototype versus a thing that actually creates a pleasant experience over hundreds of thousands of miles or millions. So
we had to wrap a lot of code around the Mobileye thing. It didn't just work by itself.
Yes, I mean that's part of the story of how you approach things. Sometimes you do things from scratch. Sometimes at first you kind of see what's out there, and then you decide to do from scratch. That was one of the boldest decisions I've seen is both on the hardware and the software to decide to eventually go from scratch. I thought, again, I was skeptical of whether that's going to be able to work out because it's such a difficult problem. And so it was an incredible journey. What I see now with everything, the hardware, the compute, the sensors, the things I maybe care and love about most is the stuff that Andrej Karpathy is leading with the data set selection, the whole data engine process, the neural network architectures, the way that's in the real world that network is tested, validated, all the different test sets, versus the ImageNet model of computer vision, like what's in academia is like real world artificial intelligence. Yeah. So,
and Andrej is awesome and obviously plays an important role, but we have a lot of really talented people driving things. So, Ashok is actually the head of autopilot engineering. Andrej is the director of AI
stuff. Yeah. So I'm aware that there's an incredible team of just a lot going on.
Yeah, just obviously people will give me too much credit and they'll give Andrej too much credit. So, and
people should realize how much is going on under the hood.
It's just a lot of really talented people. The Tesla autopilot AI team is extremely talented. It's like some of the smartest people in the world. So yeah, we're getting it done.
What are some insights you've gained over those 5-6 years of autopilot about the problem of autonomous driving? So you leaped in having some sort of first principles kinds of intuitions, but nobody knows how difficult the problem.
I thought the self-driving problem would be hard, but it was harder than I thought. It's not like I thought it would be easy. I thought it would be very hard, but it was actually way harder than even that. So, I mean, what it comes down to at the end of the day is to solve self-driving, you have to solve. You basically need to recreate what humans do to drive, which is humans drive with optical senses, eyes, and biological neural nets. And so in order to that's how the entire road system is designed to work with basically passive optical and neural nets biologically. And now that we need to, for full self-driving to work, we have to recreate that in digital form. So we have to that means cameras with advanced neural nets in silicon form. And then it will obviously solve for full self-driving. That's the only way. I don't think there's any other way.
But the question is, what aspects of human nature do you have to encode into the machine, right? So you have to solve the perception problem, like detect, and then you first realize what is the perception problem for driving, like all the kinds of things you have to be able to see. Like what do we even look at when we drive? There's I just recently heard Andrej talked about at MIT about like car doors. I think it was the world's greatest talk of all time about car doors.
Yeah.
The fine details of car doors. Like what is even an open car door, man? So like the ontology of that's the perception problem. We humans solve that perception problem, and Tesla has to solve that problem. And then there's the control and the planning coupled with the perception. You have to figure out like what's involved in driving, like especially in all the different edge cases. And then maybe you can comment on this. How much game theoretic kind of stuff needs to be involved, at a 4-way stop sign? As humans, when we drive, our actions affect the world. Like,
sure,
it changes how others behave. Most autonomous driving, you're usually just responding, to the scene, as opposed to like really, asserting yourself in the scene. Do you think?
I think these sort of control logic conundrums are not the hard part. Let's see.
What do you think is the hard part in this whole beautiful, complex problem?
So it's a lot of friggin' software, man. A lot of smart lines of code. For sure, in order to have create an accurate vector space. So, like you're coming from image space, which is like this flow of photons, going to the cameras, and and then so you have this massive bit stream in image space, and then you have to effectively compress a massive bit stream corresponding to photons that knocked off an electron in a camera sensor, and turn that bit stream into vector space. By vector space, I mean like you've got cars and humans and lane lines and curves and traffic lights and that kind of thing. Once you have an accurate vector space, the control problem is similar to that of a video game, like a Grand Theft Auto or Cyberpunk. If you have accurate vector space, it's the control problem is I wouldn't say it's trivial. It's not trivial, but it's not like some insurmountable thing. But having an accurate vector space is very difficult.
Yeah, I think we humans don't give enough respect to how incredible the human perception system is, to mapping the raw photons to the vector space representation in our heads.
Your brain is doing an incredible amount of processing, and giving you an image that is a very cleaned up image. Like when we look around here, we see, like you see color in the corners of your eyes, but actually your eyes have very few cones, like cone receptors in the peripheral vision. Your eyes are painting color in the peripheral vision. You don't realize it, but their eyes are actually painting color, and your eyes also have like this blood vessels and all sorts of gnarly things, and there's a blind spot. But do you see your blind spot? No, your brain is painting in the blind spot. And you're going to do these see these things online where you look here and look at this point, and then look at this point, and if it's in your blind spot, your brain will just fill in the missing bits.
So cool. The peripheral vision is so cool. It
Yeah.
makes you realize all the illusions for vision science. It makes you realize just how incredible the brain is.
The brain is doing a crazy amount of post-processing on the vision signals from your eyes. It's insane. So, and then even once you get all those vision signals, your brain is constantly trying to forget as much as possible. So human memory is perhaps the weakest thing about the brain is memory. So because memory is so expensive to a brain and so limited, your brain is trying to forget as much as possible and distill the things that you see into the smallest amounts of information possible. So your brain is trying to not just get to a vector space, but get to a vector space that is the smallest possible vector space of only relevant objects. And I think like you can sort of look inside your brain, or at least I can, like when you drive down the road and try to think about what your brain is actually doing consciously. And it's like you'll see a car because you don't have cameras, you don't have eyes in the back of your head or the side, so you say like you basically your head is like you basically have like two cameras on a slow gimbal. And what's your and eyesight's not that great. Okay, human eyes are, and people are constantly distracted and thinking about things and texting and doing all sorts of things they shouldn't do in a car, changing the radio station. So having arguments, is like so then like say like when's the last time you looked right and left and and rearward, or even diagonally forward, to actually refresh your vector space. So you're glancing around, and what your mind is doing is trying to distill the relevant vectors, basically objects with a position and motion, and then editing that down to the least amount that's necessary for you to drive.
It does seem to be able to edit it down or compress it even further into things like concepts. So it's like it goes beyond, the human mind seems to go sometimes beyond vector space to sort of space of concepts, to where you'll see a thing, it's no longer represented spatially somehow. It's almost like a concept that you should be aware of. Like if this is a school zone, you'll remember that as a concept. which is a weird thing to represent. But perhaps for driving, you don't need to fully represent those things, or maybe you get those kind of indirectly.
You need to like establish vector space and then actually have predictions for those vector spaces. So like like if like you drive past say a bus and you see that there's people. Before you drove past the bus, you saw people crossing, just imagine there's like a large truck or something blocking sight. But before you came up to the truck, you saw that there were some kids about to cross the road in front of the truck. Now you can no longer see the kids, but you need to be able. But you would now know, okay, those kids are probably going to pass by the truck and cross the road, even though you cannot see them. So you have to have memory. You need to remember that there were kids there, and you need to have some forward prediction of what their position will be.
It's a really hard
at
problem.
The time of relevance.
So with occlusions and computer vision, when you can't see an object anymore, even when it just walks behind a tree and reappears, that's a really, really, I mean, at least in academic literature, it's tracking through occlusions. It's very difficult.
Yeah, we're doing it.
I understand this.
Yeah.
So some of it,
it's like object permanence. Like the same thing happens with humans with neural nets. Like when like a toddler grows up, like there's a point in time where they have a sense of object permanence. So before a certain age, if you have a ball or a toy or whatever, and you put it behind your back and you pop it out, if they don't, before they have object permanence, it's like a new thing every time. It's like, whoa, this toy went poof, disappeared, and now it's back again, and they can't believe it. And that they can play peekaboo all day long because the peekaboo is fresh every time. But then we figure out object permanence. Then they realize, oh no, the object is not gone; it's just behind your back.
Sometimes I wish we never did figure out object permanence.
Yeah, so that's
an important problem to solve.
Yes, so like an important evolution of the neural nets in the car is memory across both time and space. Now you can't remember, like you have to say like how long do you want to remember things for, and there's a cost to remembering things for a long time. So you like run out of memory if you try to remember too much for too long. And then you also have things that are stale if you remember them for too long. And then you also need things that are remembered over time. So even if you, like, say, have like, for argument's sake, 5 seconds of memory on a time basis, but like let's say you're parked at a light and you saw, use a pedestrian example, that people were waiting to cross the road, and you can't quite see them because of an occlusion. But they might wait for a minute before the light changes for them to cross the road. You still need to remember that that's where they were, and that they're probably going to cross the road, type of thing. So even if that exceeds your time-based memory, it should not exceed your space memory.
And I just think the data engine side of that, so getting the data to learn all of the concepts that you're saying now, is an incredible process. It's this iterative process of there's this hydronet of many
hydronet.
Yeah.
We're changing the name to something else.
Okay, I'm sure it'll be equally as Rick and Morty like.
There's a lot of We've re-architected the neural net, neural nets in the cars so many times. It's crazy.
Oh, so every time there's a new major version, you'll rename it to something more ridiculous or memorable and beautiful. Sorry, not ridiculous, of course.
If you see the full like array of neural nets that are operating in the car, it kind of boggles the mind. There's so many layers. It's crazy. But we started off with simple neural nets that were basically image recognition on a single frame from a single camera, and then trying to knit those together with C. I should say we're really primarily running C here because C++ is too much overhead, and we have our own C compiler. So to get maximum performance, we actually wrote our own C compiler and are continuing to optimize our C compiler for maximum efficiency. In fact, we've just recently done a new rev on a C compiler that will compile directly to our autopilot hardware.
So you want to compile the whole thing down and with your own compiler.
Yeah.
Like, so efficiency here, because there's all kinds of compute. There's CPU, GPU, there's like ASIC types of things. And you have to somehow figure out the scheduling across all of those things. And so you're compiling the code down that does all, okay. So that's why there's a lot of people involved.
There's a lot of hardcore software engineering at a very sort of bare metal level. Because we're trying to do a lot of compute that's constrained to our full self-driving computer. So, and we want to try to have the highest frames per second possible in a sort of very, very finite amount of compute and power. So, we really put a lot of effort into the efficiency of our compute. So there's actually a lot of work done by some very talented software engineers at Tesla that at a very foundational level to improve the efficiency of compute and how we use the trip accelerators, which are basically doing matrix math dot products, like a bazillion dot products. And it's like what are neural nets? It's like compute wise, like 99% dot products. So,
and you want to achieve as many high frame rates, like a video game. You want full resolution, high frame rate,
low latency, low jitter. I think one of the things we're moving towards now is no post processing of the image through the image signal processor. So, like for what happens for cameras is that almost all cameras is there's a lot of post processing done in order to make pictures look pretty. Mm-hmm. And so we don't care about pictures looking pretty. We just want the data. So we're moving to just raw photon counts. So the system will, like the image that the computer sees is actually much more than what you'd see if you represented it on a camera. Wow. It's got much more data. And even in very low light conditions, you can see that there's a small photon count difference between, this spot here and that spot there, which means that, so it can see in the dark incredibly well, because it can detect these tiny differences in photon counts. That's like much better than you could possibly imagine. So, and then we also save 13 milliseconds on latency.
From removing the post processing on the image.
Yes. Yeah. It's like because we've got 8 cameras and then there's roughly 1.5 milliseconds or so, maybe 1.6 milliseconds of latency for each camera, and so going to just basically bypassing the image processor gets us back 13 milliseconds of latency, which is important. And we track latency all the way from photon hits the camera to all the steps that it's got to go through to get go through the various neural nets and the C code and there's a little bit of C++ there as well. Well, maybe a lot, but the core stuff is the heavy duty compute is all in C, and so we track that latency all the way to an output command to the drive unit to accelerate, the brakes to slow down, the steering turn left or right. So, because you got to output a command, that's got to go to a controller, and like some of these controllers have an update frequency that's maybe 10 hertz or something like that, which is slow. That's like now you lose 100 milliseconds potentially. So then we want to update the drivers on the, like say, steering and braking control to have more like 100 hertz instead of 10 hertz, and you got a 10 millisecond latency instead of 100 milliseconds worst case latency. And actually, jitter is more of a challenge than latency, because latency is like you can anticipate and predict, but But if you've got a stack up of things going from the camera to the computer, through then a series of other computers, and finally to an actuator on the car, if you have a stack up of tolerances, of timing tolerances, then you can have quite a variable latency, which is called jitter, and that makes it hard to anticipate exactly how you should turn the car or accelerate, because if you've got maybe 150, 200 milliseconds of jitter, then you could be off by up to 0.2 seconds, and this could make a big difference.
So you have to interpolate somehow to deal with the effects of jitter, so that you can make like robust control decisions. You have to. So the jitter is in the sensor information, or the jitter can occur at any stage in the pipeline.
You can, if you have fixed latency, you can anticipate, and like say, okay, we know that our information is, for argument's sake, 150 milliseconds stale. Okay. Like so, for 150 for argument's sake, 150 milliseconds from photon taken camera to where you can measure a change in the acceleration of the vehicle. So then you can say, okay, well, we're going to, we know it's 150 milliseconds, so we're going to take that into account and compensate for that latency. However, if you've got then 150 milliseconds of latency plus 100 milliseconds of jitter, which could be anywhere from 0 to 100 milliseconds on top. So then your latency could be from 150 to 250 milliseconds. Now you've got 100 milliseconds that you don't know what to do with, and that's basically random. So getting rid of jitter is extremely important.
And that affects your control decisions and all those kinds of things. Okay.
The car is just going to fundamentally maneuver better with lower jitter.
Got it.
And the cars will maneuver with superhuman ability and reaction time much faster than a human. I mean, I think over time the autopilot, full self-driving will be capable of maneuvers that are far more than what like James Bond could do in like the best movie type of thing.
That's exactly what I was imagining in my mind as you said it.
It's like impossible maneuvers that a human couldn't do. So.
Well, let me ask, sort of looking back at the 6 years, looking out into the future, based on your current understanding, how hard do you think this full self-driving problem? When do you think Tesla will solve level 4 FSD?
I mean, it's looking quite likely that it will be next year.
And what does the solution look like? Is it the current pool of FSD beta candidates, they start getting greater and greater as they have been degrees of autonomy, and then there's a certain level beyond which they can do their own, they can read a book?
Yeah. So, I mean, you can see that anybody who's been following the full self-driving beta closely will see that the rate of disengagements has been dropping rapidly. So, like a disengagement be where the driver intervenes to prevent the car from doing something dangerous potentially. So, the interventions, per million miles has been dropping dramatically. At some point, and that trend looks like it happens next year, is that the probability of an accident on FSD is less than that of the average human, and then significantly less than that of the average human. So it certainly appears like we will get there next year. Then of course then there's going to be a case of, okay, well, we now have to prove this to regulators and prove it to and we want a standard that is not just equivalent to a human, but much better than the average human. I think it's got to be at least 2 or 3 times higher safety than a human. So 2 or 3 times lower probability of injury than a human. Before we would actually say like, okay, it's okay to go. It's not going to be equivalent. It's got to be much better.
So if you look, FSD 10.6 just came out recently. 10.7 is on the way. Maybe 11 is on the way somewhere in the future.
Yeah. We were hoping to get 11 out this year, but it's 11 actually has a whole bunch of fundamental rewrites on the neural net architecture, and some fundamental improvements in creating vector space. So
there is some fundamental like leap that really deserves the 11. I mean, that's a pretty cool number.
Yeah.
You know,
11 would be a single stack for all. One stack to rule them all. And but there are just some really fundamental neural net architecture changes that will allow for much more capability, but at first they're going to have issues. So, like, we have this working on like sort of alpha software, and it's good, but it's basically taking a whole bunch of C code and deleting a massive amount of C code and replacing it with a neural net. And Andre makes this point a lot, which is like neural nets are kind of eating software. Over time, there's like less and less conventional software, more and more neural net, which is still software, but it's still comes out to lines of software. But it's just more neural net stuff and less heuristics, basically. If you're more matrix based stuff and less heuristics based stuff. Like one of the big changes will be like right now the neural nets will deliver a giant bag of points to the C++ or C and C++ code.
Yeah.
We call it the giant bag of points.
Yeah.
And it's like, so you got a pixel and something associated with that pixel. Like this pixel is probably car. This pixel is probably lane line. Then you've got to assemble this giant bag of points in the C code and turn it into vectors. And does a pretty good job of it, but we need another layer of neural nets on top of that to take the giant bag of points and distill that down to vector space in the neural net part of the software as opposed to the heuristics part of the software. This is a big improvement.
Neural nets all the way down is what you want.
It's not even all neural nets, but it's this will be just this is a game changer to not have the bag of points, the giant bag of points that has to be assembled with many lines of C++, and have a neural net just assemble those into a vector. So that the neural net is outputting much less data. It's outputting this is a lane line, this is a curb, this is drivable space, this is a car, this is a pedestrian or a cyclist or something like that. It's outputting it's really outputting proper vectors to the C++ control code as opposed to the sort of constructing the vectors in C, which we've done, I think, quite a good job of. But we're kind of hitting a local maximum on how well the C can do this. So this is really a big deal. And just all of the networks in the car need to move to surround video. There's still some legacy networks that are not surround video. And all of the training needs to move to surround video. And the efficiency of the training needs to get better, and it is. And then we need to move everything to raw photon counts as opposed to processed images.
Okay, so
which is quite a big reset on the training because the system's trained on post-processed images. So we need to redo all the training to train against the raw photon counts instead of the post-processed image.
So ultimately, it's kind of reducing the complexity of the whole thing. So reducing
lines of code will actually go lower.
Yeah, that's fascinating. So you're doing fusion of all the sensors, so reducing the complexity of having to deal with each
fusion
sensor.
of the cameras is there's not cameras really.
Right. Yes.
Yeah.
Same with humans. Well, I guess we got ears too. Okay.
Yeah, we'll actually need to incorporate sound as well because you need to like listen for ambulance sirens or fire trucks, or if somebody like yelling at you or something. I don't know. Just there's a little bit of audio that needs to be incorporated as well.
Do you need a quick bathroom break?
Yeah, let's take a break.
Okay.
Honestly, frankly, like the ideas are the easy thing, and the implementation is the hard thing. Like the idea of going to the moon is the easy part. But going to the moon is the hard part.
It's the hard part.
And there's a lot of like hardcore engineering that's got to get done at the hardware and software level. Like I said, optimizing the C compiler and just cutting out latency everywhere. Like this is, if we don't do this, the system will not work properly. So the work of the engineers doing this, they are like the unsung heroes to some, but they are critical to the success of the situation.
I think you made it clear. I mean, at least to me, it's super exciting. Everything that's going on outside of what Andre is doing.
Yeah.
Just the whole infrastructure, the software. I mean, everything is going on with data engine, whatever it's called. The whole process is just a work of art to me.
The sheer scale of it is boggles the mind. Like the training, the amount of work done with, like we've written all this custom software for training and labeling, and to do auto labeling. Auto labeling is essential, because especially when you've got like surround video, it's very difficult to like label surround video from scratch is extremely difficult. It like take a human such a long time to even label one video clip, like several hours. Or the auto labeler, basically we just apply heavy duty, like a lot of compute to the video clips, to pre-assign and guess what all the things are that are going on in the surround video.
And then there's like correcting it.
Yeah, and then all the human has to do is like tweet, like say this, adjust what is incorrect. This is like increases productivity by 100 or more.
Yeah. So you've presented Tesla Bot as primarily useful in the factory. First of all, I think humanoid robots are incredible. From a fan of robotics, I think the elegance of movement that humanoid robots, the bipedal robots show are just so cool. So it's really interesting that you're working on this and also talking about applying the same kind of all the ideas of some of which we've talked about with data engine, all the things that we're talking about with Tesla Autopilot, just transferring that over to just yet another robotics problem. I have to ask, since I care about human-robot interaction, so the human side of that. So you've talked about mostly in the factory. Do you see it also? Do you see part of this problem that Tesla Bot has to solve is interacting with humans and potentially having a place like in the home? So interacting, not just not replacing labor, but also like, I don't know, being a friend or an assistant.
Yeah,
or something like that.
I think the possibilities are, endless. Yeah, I mean, it's obviously like it's not quite in Tesla's primary mission direction of accelerating sustainable energy, but it is an extremely useful thing that we can do for the world, which is to make a useful humanoid robot that is capable of interacting with the world and helping in many different ways. So in factories and really just I mean, I think if you say like extrapolate to many years in the future, it's like I think work will become optional. So like there's a lot of jobs that if people weren't paid to do it, they wouldn't do it. Like it's not fun, necessarily. Like if you're washing dishes all day, it's like even if you really like washing dishes, you really want to do it for 8 hours a day every day? Probably not. So and then there's like dangerous work, and basically if it's dangerous, boring, it has like potential for repetitive stress injury, that kind of thing, then that's really where humanoid robots would add the most value initially. So that's what we're aiming for is to for the humanoid robots to do jobs that people don't voluntarily want to do. And then we'll have to pair that obviously with some kind of universal basic income in the future. So I think.
So do you see a world when there's like hundreds of millions of Tesla bots performing different tasks throughout the world?
Yeah, I haven't really thought about it that far into the future, but I guess that there may be something like that. So,
Can I ask a wild question? So, the number of Tesla cars has been accelerating. There's been close to 2 million produced. Many of them have autopilot.
I think we're over 2 million now. Yeah.
Do you think there will ever be a time when there will be more Tesla bots than Tesla cars?
Yeah, actually, it's funny you asked this question because normally I do try to think pretty far into the future, but I haven't really thought that far into the future with the Tesla bot, or it's codenamed Optimus. I call it Optimus Subprime because it's not like a giant transformer robot. But it's meant to be a general purpose helper bot. And basically like the things that we're basically like Tesla, I think has the most advanced real world AI for interacting with the real world, which we developed as a function of to make self-driving work. And so along with custom hardware and like a lot of hardcore low-level software to have it run efficiently and be power efficient, because it's one thing to do neural nets if you've got a gigantic server room with 10,000 computers, but now let's say you have to now distill that down into one computer that's running at low power in a humanoid robot or a car. That's actually very difficult, and a lot of hardcore software work is required for that. So since we're kind of like solving the navigate the real world with neural nets problem for cars, which are kind of like robots with four wheels, then it's like kind of a natural extension of that is to put it in a robot with arms and legs, and actuators. Like the two like hard things are like you basically need to have the robot be intelligent enough to interact in a sensible way with the environment. So you need real world AI, and you need to be very good at manufacturing, which is a very hard problem. Tesla's very good at manufacturing, and also has the real world AI. So making the humanoid robot work is basically means developing custom motors and sensors that are different from what a car would use. But we have I think we have the best expertise in developing advanced electric motors and power electronics.